In this video, we're going to talk about function notation. Function notation refers to notation such as f of x used to represent the value of the dependent variable, i.e. the output, for a given value of the independent variable x, i.e. the input. In other words, f of x is the output obtained from the function f when the input is x. Now, usually we consider the output to be y when the input is x. Think back to grade 9 math, if you will. If we gave you something like this, y equals 2x plus 4, we instructed you build yourself a table of values, and then we said pick a few values for x and input them to this formula. So if you were to input the number 0 in for x, y would be 2 times 0 plus 4, which is 0 plus 4, which is 4. Then you would say the output was y, which is 4. Then you would input a different value for x. You would input 1. When you input the 1, you would then determine what the output was, and you called the output y. And when you input the next x value, you got a new output. Well, instead of calling those outputs y, we sometimes call them f of x, and then we say y equals f of x. So it's kind of a roundabout way of getting to the same place. But it's just important to remember that in this context, that is not multiplication. It's not f times x. F is not a variable. Rather, it's something describing an entire function operating on an independent variable. So let's do a few examples here. Suppose we wanted to evaluate f at negative 4. Well, I go to where x is negative 4, and I see when x is negative 4, the point on the function is the point negative 4, negative 1. Since y is equal to f of x, then that means the y coordinate, which is negative 1, equals f of the x coordinate, which is negative 4. So quite simply, f at negative 4 equals negative 1. And that's the final answer. You're literally just looking on the function for what is the what is the y coordinate when the x coordinate is negative 4. Okay? So, since the point negative 4, negative 1 is part of the function f, therefore f at negative 4 equals negative 1. Well, let's evaluate f at 1. Using the same strategy, we know that the function contains the point 1, 2, so that means f at 1 equals 2. Pretty straightforward. Okay, it takes some getting used to though. F at 1 equals 2. Now, this is a trick question. F at negative 1. What we're saying is, where on this function is there an x value of negative 1? The answer is there isn't anywhere an x value of negative 1. So we can simply say f at negative 1 does not exist. Okay? So there is no point with an x value of negative 1. Therefore, f at negative 1 does not exist. Now, let's try one a little bit more complicated. When you get a question like this, sometimes people make a mistake. They want to distribute the 3 in. I'll show you the wrong thing to do. The wrong thing would be to multiply the 3 and the negative 5 and call it f of negative 15. That's wrong, but I've seen people try to do it. Instead, try to find, when you have a question like this, try to evaluate f at negative 5 and then try to evaluate f at 0. Get those function values without even thinking about the expression that it's part of. So looking at this right here, f at negative 5, I go on this function to where there's x value of negative 5. There's an x value of negative 5 down here where the y value is negative 1. So I know right away f at negative 5 equals negative 1. Then for f at 0, I go on this function where there's an x coordinate of 0, and that's up here. When the x coordinate is 0, the y coordinate is 2. So that means f at 0 equals 2. Okay, so now I come back over to this expression, and now that I know what these values are, I can sub them in. F at -5, what I've circled right here, is simply equal to -1. So I can say that this is 3 times -1 minus 2. And then we said a minute ago f at 0 is 2. So this f at 0 is a 2. And so my answer is 3 times -1 minus 2 times 2, which is -3 minus 4, which is -7. So that's the answer. And this is the answer a little bit more neatly written if you want to screenshot it and see it that way. All right, now, what if you have a function equation rather than a graph? So suppose we tell you f of x equals 3x squared minus 7x plus 4. If we tell you f of x is 3x squared minus 7x plus 4, what we're really saying is f at block is 3 block squared minus 7 block plus 4. And we can plug anything into that block. So if it's an x, then this expression reads, if you put an x there, then it becomes 3x squared minus 7x plus 4. But instead of an x, what if I put a 5 there? That's pretty simple. If you put a 5 there, then just plug a 5 in for that block. And if this is what you have, you can now simply evaluate f at 5 by using some Bedmes principles that you learned in earlier grades. Okay? So 3 times 5 squared, we do the exponent first. We would get, 5 squared would actually be 25. Little mistake here. And then minus 35 plus 4. So we would have, I made a little typo here. 3 times 25 would be 75. Sorry about that. Let me just redo this here. I made a little arithmetic error there. We would have 5 squared. What I'm circling here is our first operation we should do. 5 squared is 25, so we would get 3 times 25. Then the 7 times 5 is 35, minus 35, plus 4. Okay, and so now we would just evaluate that. 75 minus 35 plus 4, that would be altogether 44. So that should be our final answer, not 344. Made a little typo there, or a little arithmetic error, I should say. Now, what if we have something much more complicated like this? It doesn't have to be all that complicated. We just have to be very patient with it. We're going to want to evaluate g at 1/3, and it's going to take some patience, but you've done this sort of work in previous grades where you evaluate a long expression like that. And then we're also going to want to evaluate g at -1/5, and we're just going to take our time, find common denominators, be really disciplined in our approach, and when we do all that, we'll get the right answer for that. And after we spend time evaluating those two expressions, we'll be able to put them in and do the final evaluation. So the moral here is, when you see something complicated like what I'm circling right now, find each function value. Find g at 1/3, take your time. Find g at -1/5, take your time. If you try to rush through it, that's when you'll make mistakes. So we figure those out separately. I won't go through them step by step, but plugging in x value of 1/3 to this expression gives us ultimately an answer of -11/7 by using disciplined fraction steps. And plugging in x value of -1/5 to that same expression ultimately leads to a value of -21/17. So what that means, since g at 1/3 is equal to -11/7, that means I can just plug that in. And since g at negative a fifth is equal to negative 21 over 17, but I'm subtracting 2 of those, I can say minus 2 times negative 21 over 17, and then I'll just be able to evaluate that using fraction rules. And when we do all of that, it's on the screen in front of you, we ultimately get 107 over 119. Okay, now, what if we have a situation like what you see in front of you? We want to evaluate 3g at 4 minus 5f of negative 2. So first thing we want to do is figure out what does g at 4 equal. And then we want to figure out what does f at negative 2 equal. Well, we figure out what g at 4 equals by plugging in a 4 there. We figure out what f at negative 2 equals by plugging in a negative 2 there. So g at 4 ultimately equals 17, and f at negative 2 ultimately equals 23. Okay, so now that we have them, then what we can do is look at this original thing and say, since g at 4 is simply 17, instead of 3 times g at 4, I can call it 3 times 17. And then since f at negative 2 is ultimately equal to 23, I can simply say minus 5 times 23. And what we end up with is 51 minus 115, which is negative 64. So just spotted another little typo here. That should be 115, not 105. Because 5 times 23 is 115. And so then 51 minus 115 is ultimately negative 64. So another little calculation error, but the process overall in both of these questions was correct. Okay, now what if we wanted to determine a simplified expression for f of 2a minus 1? So this is a situation where it's helpful to think in terms of block. When we see f of x, we can call it f of block. So then when we see 4x squared, we can think of that as 4 block squared. And then minus 5x, we can think of as minus 5 block. And then plus 8. And so when we're looking for f at 2a minus 1, that instead of calling it f at block, we call it f at 2a minus 1. What that really means is the block is 2a minus 1. So that means that block should be 2a minus 1. And that means that block should be 2a minus 1. And then what we have to do is just make sure we put those 2a minus 1s next to each other, the ones that we're expanding out. We want to distribute that negative 5 in here. And then we'll be in a position where we can actually just expand and collect like terms. And we'll show that on the next slide. So like we showed, this is where we left off the last slide. When you expand this 2a minus 1 times 2a minus 1, you end up with the long expression shown here. We distribute that negative 5 into this bracket. It becomes negative 10a plus 5. We still have that plus 8 on the end. And now we want to distribute in the 4. Okay. And we still have the minus 10a plus 5 plus 8. And we get to this point right here, and now we just want to collect like terms. We have 16a squared, negative 8a, negative 8a, negative 10a, so that's negative 26a, plus 4, plus 5, plus 8 becomes plus 17. And for this question, this one's a little bit different. In this question, we're being told that 2f of a equals a minus 1. Well, let's start by looking at f of a. Let's look at that function part first. If f of x is 6x squared plus 10x minus 11, then that means f of a must be 6a squared plus 10a minus 11. Well, if 2f of a is on the left-hand side, then that means the left-hand side is 2 6a squared plus 10a minus 11. And it equals a minus 1. There we go. And now what we're going to do after this, we're just going to expand that 2 in. And then we'll have a long quadratic on the left. We're then going to be able, in the next step after that, to bring the a over and the -1 over, and we'll have a long quadratic on the left and the right-hand side equaling 0. We'll then be in a position to either factor or use the quadratic formula. And that's what happens here. F of a is this expression, so 2f of a becomes 12a squared plus 20a minus 22. Setting that equal to a minus 1, I should say a minus 1 here. Setting that equal to a minus 1 is shown in this step. Subtract a from both sides, add 1 to both sides, we get this. And then we can factor both sides. We can factor the left, or we could use the quadratic formula, whatever we choose. And we would ultimately get two values for a as shown at the bottom. And now we've answered the question. When the question says solve for a, that means they want us to give one or more values, all the values possible for a.